Hello, my name is Josiah Hanna, and I'm an assistant professor in CS at UW-Madison. And here I'm part of the department's machine learning and robotics research groups. So the research questions which fascinate me kind of all come back to this fact that I'm fascinated by the ability of people and animals to acquire rich capabilities from their experience. So human and animal babies, they begin life with kind of very few capabilities and rather helpless, but then over time they become amazingly proficient at a wide number of skills. And of course, there's some question about nurture versus nature, but I think undeniably a large part of this is that they learn from experience. And so, as a computer scientist, I want to understand how we can recreate the same ability to learn over time in computers and robots. So the big question that drives my research is how can autonomous agents learn goal-directed behaviors from experience? So a lot of my work contributes to the field of reinforcement learning, or RL for short. And my research interests in this space are very broad, but I like to organize them into three kind of core research thrusts. So first, my group thinks a lot about RL algorithms and how we can make today's algorithms more data efficient and more able to be applied to real problems. So this kind of spans from both fundamental algorithmic work to more practical techniques like data augmentation and sim to real. Also, trustworthy RL is really important. How do we give stakeholders and practitioners confidence that learned decision making will actually improve performance on some target domain? And then finally, we think a lot about challenge problems for RL. So domains where it has been difficult to apply reinforcement learning for a variety of reasons, and then we try to develop the capabilities to enable success there. So I'll talk a little bit more about each of these areas. Just really quick, if you're not familiar with reinforcement learning already, the idea is that we're modeling a really kind of general sequential decision-making process where we have an agent able to take actions to influence the state of some environment that it's situated in. Taking actions produces reward for the agent and also moves the agent to a new state. And so the goal in reinforcement learning is to find what's called a policy, or just a mapping from states of the world to actions to take, which will maximize the total discounted reward that the agent receives over time. So this is very general and it's applicable from robotics to web marketing to healthcare to many different domains. So the first thrust of my research is that we think about developing new RL algorithms and new techniques for applying reinforcement learning. In a sense, we would like reinforcement learning to be as used off the shelf as a lot of like supervised learning and other types of machine learning are. And this will enable practitioners to build learning agents in kind of really any new domain. So some of our recent work in this area has looked at efficient exploration, as well as how to learn with really abstract representations of the world. There's also some work we've been doing in representation learning, how to handle partial observability, as well as learning models of an agent's environment. The second thrust of the work is thinking about trustworthy RL algorithms. The high level goal is that we want to enable practitioners to be really confident when they deploy learned decision making in their domain that what the new decision making is going to be, at least as good as what they were doing before, if not better. One main way that we've looked into doing this is through a type of method called offline policy evaluation. The idea being that in many domains, you can collect historical data of how decisions were made in the past. And then when you have a new but untested decision-making policy produced by a reinforcement learning algorithm, you can ask that counterfactual question of what if this new policy had been making decisions in the past instead of whatever policy we used. In this sense, we can use data to score how well we think a policy would perform before we actually deploy it. And through these methods, we would be able to decide, is this policy safe enough to deploy in our domain? The final thrust in the work is challenge problems for RL. And so the idea here is that we want to find domains where RL is difficult to apply and develop methods that enable its application. Recently, we've been doing work in robot soccer. Robot soccer is a very challenging multi-agent problem where agents have to reason with a high degree of partial observability. It's multi-agent, adversarial, and it's very difficult to collect enough experience for learning. Our work recently has been showing how reinforcement learning can be applied in this domain. We've also done work in other applications such as transportation systems, autonomous driving, material synthesis, and robot locomotion. So anytime there's a good domain that challenges what today's reinforcement learning algorithms can do, it's one we want to look at. So that's my research in a nutshell. If you have any questions for it, feel free to get in touch with me by email here, or you can check out the related publications on my webpage here. Thank you.